Alright, so here we go with iChem lesson 20 on colligative properties. Colligative properties is a funny thing to say, kind of a weird word, but it's a pretty simple equation to apply. This is the only time really we're going to be using molality in any sort of calculation. But first let's apply some definitions. So colligative properties tells us that a solution will have different physical properties than the physical properties of the solvent due to the presence of the solute particles. The number of solute particles determines the severity of the properties change. So the number of solute particles determines how big of a difference between the properties there is. There are two main colligative properties that we're going to talk about. The first one is freezing point depression. In layman terms, it basically just means a decreased depression in freezing point. The freezing point of a solution will be lower than the normal freezing point of the solvent. So if you add, for example, salt to water, the salt will freeze at a much lower temperature than pure water. This is something we do all the time in the winters. Not as much around here as back at home, but we salt the roads to change the freezing point of water so that the roads don't ice over as readily and we can drive more safely in cold temperatures, especially cold and wet temperatures. The opposite is true for the boiling point. The boiling point will elevate, the boiling point elevation. The boiling point of a solution will be higher than the normal boiling point of the solvent. Again, add salt to water, the salt water will boil at a higher temperature than pure water. The equations that go with this are equations for freezing point and boiling point change in temperature. They look pretty similar. We're going to run through the freezing point one first. So first, if you look at this equation, here it is. If you look at this equation, you see that you find the change in temperature. This is the amount that the temperature decreases by is equal to this constant. This will be given to you for the solvent, freezing point constant, times the molality, this we can calculate, times the number of ions present in the solute. Don't worry if you didn't get all of this equation down. It'll be up on the next slide when we start to use it, but before we do that, I'm going to talk more about how you find this I, because this is this number of ions present is a new concept. So we sort of know the background for it already. In ionic solutes dissociate into ions when they dissolve. So remember, if we put salt, for example, sodium chloride into water, it's not going to be just sodium chloride, it's going to be a sodium ion, and a chlorine ion. So in reality what you have is 2 ions for every 1 sodium chloride, so the I is 2. If I dissociate magnesium chloride, I'll have 1 magnesium ion and 2 chlorine ions, because the subscript here is a 2. So in total, I'll have 3 ions. For magnesium hydroxide, again, 1 magnesium and 2 hydroxides. We count the hydroxide together as a single ion, just like we did with chlorine. For covalent solutes, they do not dissociate as they dissolve. So for all covalent solutes, I equals 1. Alright, so let's look back at the equation and start to apply the concepts. So here's the equation again. The change in temperature you get by multiplying the constant times the molality times the number of ions. The constant will be given to you, so we already have the constant down here. Let's see if we can get the other pieces of information we need. We're interested in finding what the new freezing point will be when 15 grams of sodium chloride is dissolved in 200 milliliters of water. Okay. we need molality. We have the information we need to get it, but we don't quite have it yet. I need, if we draw our triangle to find molality, I need moles of solute and kilograms of solvent. This last part is relatively easy. My solvent is water. I have 200 milliliters. That's the same thing as saying 200 grams. So if I want kilograms, I just divide by 100 and get, 0.2 kilograms. I'll get better at using this thing eventually. All right, so I have my kilograms, now I need to get my moles. I have 15 grams of sodium chloride. To convert that to moles, grams goes down here, moles goes up here. That's my molar mass. It's always per 1 mole, the molar mass of sodium chloride I get by adding the molar masses of sodium and chlorine together. And I calculate this 15 divided by 58.5. I get 0.256 moles. Okay, so now I have moles and I have kilograms. I can find molality. I cover up the M, I see molality is moles divided by kilograms. So I take my moles from here and I divide by my kilograms. I end up with 1.28 molal solution. Okay, so now I have molality. I need my number of ions. We did sodium chloride already. If you remember, it will break up into 1 sodium and 1 chlorine. So add that together. I have 2 ions altogether. Now I have everything I need in my equation for delta T. So delta T is equal to Kf, which is down here, 1.86 times the molality, which is 1.28, times I, which is 2. My change in temperature then is 4.76 degrees Celsius. Now I need to think about this for a minute. I'm asked what the new freezing point is. Freezing point depression. So the freezing point is going to decrease by this amount. So what's the starting freezing point? Well, the freezing point of the solvent, water, is 0 degrees. And then it's going to decrease by, so minus 4.76 degrees Celsius. So your new freezing point is negative 4.76 degrees Celsius. Let's do another example. Now we're doing boiling point elevation. So the change in temperature for boiling, the equation looks very similar, except now I have a different constant. From boiling, I'm going to use the Kb, the constant, the boiling constant for water is down here. So same things again though. I can actually just use the information from the previous slide. I have my my grams, same volume of water, so it'll be the same molality from before. So if we go back, we found it by taking the molar mass, or taking the grams and using the molar mass to find moles, dividing the moles by number of kilograms to get a molality of 1.28. why sodium chloride dissociates into 2 ions. So my delta T of boiling is Kb times the molality times the number of ions. So 0.52 times 1.28 times 2. Your change in temperature is 1.33 degrees. So boiling point elevation, the change in temperature is a positive number. It increases. So I need to figure out my new boiling point. I'm starting at 100 and I'm elevating by 1.33. So my new temperature for boiling point is 101.3 degrees Celsius. Don't forget this last step. Just because you calculate delta T doesn't mean you have your answer. Alright, one more application. This is more of a design approach, an engineering application. And do this, think about it as, how would I know that it's going to be -8 degrees outside tonight. How much salt do I need to add to change the freezing temperature of the water? Okay, so I have my volume, but I don't have anything to find the molality. Let's write my equation up here again. I have delta T, for freezing, equals K freezing times molality times I. What do I know? Well, I know I still, for sodium chloride, is 2. I can find that Kf constant back on a previous slide or in my notes as 1.86 degrees Celsius per mole. Okay. And actually this time I know my change in temperature to be -8 degrees, so I know delta T. So I need to plug this into the equation. So delta T is 8 times Kf, which is 1.86, times molality, that I don't know, times 2. So I can solve this equation for molality. Divide by 1.86, times 2 on both sides. So molality equals 8 divided by 1.86 times 2, 2.15. Now I know molality, and I know how much water I have. In the equation for molality, I need kilograms of water. All right, if you look at the triangle, horrible triangle, but you get the point. Molality, kilograms, and moles. I can find moles by multiplying molality times kilograms. How many kilograms do I have? Well, I have about 200 milliliters. So I have 0.2 kilograms. All right. So moles, I do 2.15 times 0.2. That gives me 0.43 moles of sodium chloride. And now all I'm left with is to convert that